A spacesuit is a garment worn to keep a human alive in the harsh environment of outer space. Vacuum and temperature extremes. Spacesuits are often worn inside spacecraft as a safety precaution in case of loss of cabin pressure, and are necessarily for extravehicular activity, work done outside spacecraft. Spacesuits have been worn for such work in Earth orbit, on the surface of the Moon, and en route back to Earth from the Moon. Modern spacesuits augment the basic pressure garment with a complex system of equipment and environmental systems designed to keep the wearer comfortable, and to minimize the effort required to bend the limbs, resisting a soft pressure garment's natural tendency to stiffen against the vacuum. A self-contained oxygen supply and environmental control system is frequently employed to allow complete freedom of movement, independent of the spacecraft. Three types of spacesuits exist for different purposes: EVA, and IEVA. EVA suits are meant to be worn inside a pressurized spacecraft, and are therefore lighter and more comfortable. IEVA suits are meant for use inside and outside the spacecraft, such as the Gemini G4C suit. They include more protection from the harsh conditions of space, such as protection from micrometeorites and extreme temperature change. EVA suits, such as the EMU, are used outside spacecraft for either planetary exploration or spacewalks. They must protect the wearer against all conditions of space, as well as provide mobility and functionality. Some of these requirements also apply to pressure suits worn for other specialized tasks, such as high-altitude reconnaissance flight. Above Armstrong's line, the atmosphere is so thin that pressurized suits are needed. The first full pressure suits for use at extreme altitudes were designed by individual inventors as early as the 1930s. The first space suit worn by a human in space was the Soviet SK-1 suit worn by Yuri Gagarin in 1961. Requirements. A spacesuit must perform several functions to allow its occupant to work safely and comfortably inside or outside a spacecraft. It must provide a stable internal pressure. This can be less than Earth's atmosphere, as there is usually no need for the spacesuit to carry nitrogen. Lower pressure allows for greater mobility, but requires the suit occupant to breathe pure oxygen for a time before going into this lower pressure, to avoid decompression sickness. Mobility. Movement is typically opposed by the pressure of the suit. Mobility is achieved by careful joint design. See the Theories of Spacesuit Design section. Supply of breathable oxygen and elimination of carbon dioxide. These gases are exchanged with the spacecraft or a portable life support system. Temperature regulation. Unlike on Earth, where heat can be transferred by convection to the atmosphere, in space, heat can be lost only by thermal radiation or by conduction to objects in physical contact with the exterior of the suit. Since the temperature on the outside of the suit varies greatly between sunlight and shadow, the suit is heavily insulated, and air temperature is maintained at a comfortable level. A communication system with external electrical connection to the spacecraft, a PLSS, means of collecting and containing solid and liquid bodily waste. Optional requirements. Advanced suits better regulate the astronaut's temperature with a liquid cooling and ventilation garment in contact with the astronaut's skin, from which the heat is dumped into space through an external radiator in the PLSS. Additional requirements for EVA include shielding against ultraviolet radiation, limited shielding against particle radiation, means to maneuver, dock, release, and/or tether onto a spacecraft, protection against small micrometeoroids, some traveling at up to 27,000 km per hour, provided by a puncture-resistant thermal micrometeoroid garment, which is the outermost layer of the suit. Experience has shown the greatest chance of exposure occurs near the gravitational field of a moon or planet. so these were first employed on the Apollo lunar EVA suits. As part of astronautical hygiene, control of space suit is essential for extravehicular activity. The Apollo Skylab A7L suit included 11 layers in all: an inner liner, ALCVG, a pressure bladder, a restraint layer, another liner, and a thermal micrometeoroid garment consisting of 5 aluminized insulation layers and an external layer of white ortho fabric. This space suit is capable of protecting the astronaut from temperatures ranging from -156 degrees Celsius to 121 degrees Celsius. During exploration of the Moon and Mars, there will be the potential for lunar, Martian dust to be retained on the space suit. When the space suit is removed on return to the spacecraft, there will be the potential for the dust to contaminate surfaces and increase the risks of inhalation and skin exposure. Astronautical hygienists are testing materials with reduced dust retention times and the potential to control the dust exposure risks during planetary exploration. Novel ingress-egress approaches, such as suit ports, are being explored as well. In NASA space suits, communications are provided via a cap worn over the head, which includes earphones and a microphone. Due to the coloration of the version used for Apollo and Skylab, which resembled the coloration of the comic strip character Snoopy, these caps became known as Snoopy caps. Operating pressure generally to supply enough oxygen for respiration. A space suit using pure oxygen must have a pressure of about 32.4 kilopascals, equal to the 20.7 kilopascals partial pressure of oxygen in the Earth's atmosphere at sea level, plus 5.3 kilopascals CO2 and 6.3 kilopascals water vapor pressure, both of which must be subtracted from the alveolar pressure to get alveolar oxygen partial pressure in 100% oxygen atmospheres, by the alveolar gas equation. The latter two figures add to 11.6 kilopascals, which is why many modern space suits do not use 20.7 kilopascals, but 32.4 kilopascals. In space suits that use 20.7 kilopascals, the astronaut gets only 20.7 kilopascals minus 11.7 kilopascals equals 9.0 kilopascals of oxygen, which is about the alveolar oxygen partial pressure attained at an altitude of 1,860 meters above sea level. This is about 78% of normal partial pressure of oxygen at sea level, about the same as pressure in a commercial passenger jet aircraft, and is the realistic lower limit for safe ordinary space suit pressurization, which allows reasonable capacity for work. When space suits below a specific operating pressure are used from craft that are pressurized to normal atmospheric pressure, this requires astronauts to pre-breathe before donning the suits and depressurizing in the airlock. This procedure purges the body of dissolved nitrogen, so as to avoid decompression sickness due to rapid depressurization from a nitrogen-containing atmosphere. Exposure to space without a space suit. The human body can briefly survive the hard vacuum of space unprotected. Despite contrary depictions in some popular science fiction, human flesh expands to about twice its size in such conditions, giving the visual effect of a bodybuilder rather than an overfilled balloon. Consciousness is retained for up to 15 seconds as the effects of oxygen starvation set in. No snap freeze effect occurs because all heat must be lost through thermal radiation of the evaporation of liquids, and the blood does not boil because it remains pressurized within the body. In space, there are many different highly energized subatomic protons that will expose the body to extreme radiation. Although these compounds are minimal in amount, the high energy is liable to disrupt essential physical and chemical processes in the body, such as altering DNA or causing cancers. Exposure to radiation can create problems via two methods. The particles can react with water in the human body to produce free radicals that break DNA molecules apart, or by directly breaking the DNA molecules. Temperature in space can vary extremely depending on where the sun is. Temperatures from solar radiation can reach up to 250 degrees Fahrenheit and lower down to -387 degrees Fahrenheit. Because of this, spacesuits must provide proper insulation and cooling. The vacuum in space creates zero pressure, causing the gases and processes in the body to expand. In order to prevent chemical processes in the body from overreacting, it is necessary to develop a suit that counteracts against the pressure in space. The greatest danger is in attempting to hold one's breath before exposure, as the subsequent explosive decompression can damage the lungs. These effects have been confirmed through various accidents. Human skin does not need to be protected from vacuum and is gas-tight by itself. Instead, it only needs to be mechanically compressed to retain its normal shape. This can be accomplished with a tight-fitting elastic bodysuit on a helmet for containing breathing gases known as a space activity suit. Contributing technologies. Related preceding technologies include the gas mask used in World War II, the oxygen mask used by pilots of high-flying bombers in World War II, the high-altitude vacuum suit required by pilots of the Lockheed U-2 and State Route 71 Blackbird, the diving suit, rebreathed scuba diving gear, and many others. Many spacesuit designs are taken from the U.S. Air Force suits, which are designed to work in high-altitude aircraft pressure, such as the Mercury EVA suit of the Gemini G4C, or the Advanced Crew Escape suits. Gloves technology. The Mercury EVA, the first U.S. spacesuit design, included lights at the tips of the gloves in order to provide visual aid. As the need for extravehicular activity grew, suits such as the Apollo A7L included gloves made of a metal fabric called chromela in order to prevent punctures. In order to retain a better sense of touch for the astronauts, the fingertips of the gloves were made of silicone. With the shuttle program, it became necessary to be able to operate spacecraft modules, so the ACE suits featured gripping on the gloves. EMU gloves, which are used for spacewalks, are heated to keep the astronauts' hands warm. The Phase 6 gloves, meant for use with the Mark III suit, are the first gloves to be designed with laser scanning technology, 3D computer modeling, stereolithography, laser cutting technology, and CNC machining. Quote, "This allows for cheaper, more accurate production, as well as increased detail in joint immobility and flexibility." Life support technology. Prior to the Apollo missions, life support in spacesuits was connected to the space capsule via an umbilical cord-like device. However, with the Apollo missions, life support was configured into a removable capsule called the Portable Life Support System that allowed the astronaut to explore the Moon without having to be attached to the spacecraft. The EMU spacesuit, used for spacewalks, allows the astronaut to manually control the internal environment of the suit. The Mark III suit has a backpack filled with about 12 pounds of liquid air, as well as pressurization and heat exchange. Helmet technology. The development of the spheroidal dome helmet was key in balancing the need for field of view, pressure compensation, and low weight. One inconvenience with some spacesuits is the head being fixed facing forwards and being unable to turn to look sideways. Astronauts call this effect alligator head. High-altitude suits. Evgeny E. Chertovsky created his full-pressure suit, a high-altitude scaphandre, in 1931. Emilio Herrera Linares designed and built a full-pressure suit, Escafandra Astronautica, in 1935, which was to have been used during an open-basket balloon stratospheric flight scheduled for early 1936. Wiley Post experimented with a number of pressure suits for record-breaking flights. Russell Coley created the space suits worn by the Project Mercury astronauts, including fitting Alan Shepard for his ride as America's first man in space on May 5, 1961. Models of historical significance. Soviet and Russian suit models SK series, the space suit used for the Vostok program, worn by Yuri Gagarin on the first manned spaceflight. No-pressure suits were worn aboard Voskhod-1. Burkett. The space suit was a modified SK-1 used by the crew of Voskhod-2, which included Alexei Leonov on the first spacewalk during. From Soyuz 1 to Soyuz 11, no-pressure suits were worn during launch and re-entry. Jastreb extravehicular activity space suit used during a crew exchange between Soyuz 4 and Soyuz 5. KRECHET-94 spacesuit, designed for the cancelled Soviet manned moon landing. Strige spacesuit developed for pilots of the Buran space shuttle. Sokol suits worn by Soyuz crew members during launch and re-entry. They were first worn on Soyuz 12. They have been used from 1973 to present. All-in suits for extravehicular activity, originally developed for the Soviet lunar program as a lunar orbit EVA suit. It is Russia's current EVA suit, used from 1977 to present. United States suit models. In the early 1950s, Siegfried Hansen and colleagues at Litton Industries designed and built a working hard-shell suit, which was used inside vacuum chambers and was the predecessor of space suits used in NASA missions. Navy Mark IV high-altitude vacuum suit used for Project Mercury. Gemini spacesuits. There were three main variants developed: G3C designed for intravehicle use, G4C specially designed for EVA and intravehicle use, and a special G5C suit worn by the Gemini 7 crew for 14 days inside the spacecraft. Manned Orbital Laboratory MH7 spacesuits for the cancelled MOL program. Apollo Block IA-1C suit was a derivative of the Gemini suit worn by primary and backup crews in training for two early Apollo missions. The nylon pressure garment melted and burned through in the Apollo 1 cabin fire. This suit became obsolete when manned Block I Apollo flights were discontinued after the fire. Apollo, Skylab A7L EVA and Moon suits. The Block II Apollo suit was the primary pressure suit worn for 11 Apollo flights, 3 Skylab flights, and the U.S. astronauts on the Apollo-Soyuz test project between 1968 and 1975. The pressure garment's nylon outer layer was replaced with fireproof beta cloth after the Apollo 1 fire. This suit was the first to employ a liquid-cooled inner garment and outer micrometeoroid garment. Shuttle ejection escape suit used from SDS-1 to SDS-4 by a two-man crew used in conjunction with the then-installed ejection seats, derived from a USAF model. These were removed once the shuttle became certified. From SDS-5 to SDS-25, no-pressure suits were worn during launch and re-entry. A crew would wear only a blue flight suit with an oxygen helmet. Launch entry suit first used on SDS-26, the first flight after the Challenger disaster. It was a partial pressure suit derived from a USAF model. It was used from 1988 to 1998. Advanced crew escape suit used on the Space Shuttle starting in 1994. The Advanced Crew Escape Suit, or ACES suit, is a full-pressure suit worn by all Space Shuttle crews for the ascent and entry portions of flight. The suit is a direct descendant of the United States Air Force high-altitude pressure suits worn by State Route 71 Blackbird and U-2 spyplane pilots, North American X-15 and Gemini pilot astronauts, and the launch entry suits worn by NASA astronauts starting on the STS-26 flight. It is derived from a USAF model extravehicular mobility unit used on both the Space Shuttle and International Space Station. The EMU is an independent anthropomorphic system that provides environmental protection, mobility, life support, and communications for a Space Shuttle or ISS crew member to perform an EVA in Earth orbit. Used from 1982 to present. Chinese suit models: Shuguang spacesuit, first-generation EVA spacesuit developed by China for the 1967 cancelled Project 714 manned space program, with a mass of about 10 kilograms of orange color, made of high-resistance multi-layers polyester fabric. The astronaut could use it inside the cabin and conduct an EVA as well. Project 863 spacesuit, cancelled project of second-generation Chinese EVA spacesuit. Shenzhou EVA spacesuit. The suit was first worn by Yang Liwei on Shenzhou 5, the first Chinese spaceflight. It closely resembles a Sokol KV-2 suit, but it is believed to be a Chinese-made version rather than an actual Russian suit. Pictures show that the suits on Shenzhou 6 differ in detail from the earlier suit. They are also reported to be lighter. Haring EVA spacesuit. The imported Russian Orlan-M EVA suit is called Haring. Used on Shenzhou 7. Fashioned EVA spacesuit. New generation indigenously developed Chinese-made EVA spacesuit also used for the Shenzhou 7 mission. The suit was designed for a spacewalk mission of up to 7 hours. Chinese astronauts have been training in the out-of-capsule spacesuit since July 2007, and movements are seriously restricted in the suits, with a mass of more than 110 kilograms each. Emerging technologies. Several companies and universities are developing technologies and prototypes which represent improvements over current spacesuits. Z-Series. In 2012, NASA introduced the Z-1 spacesuit, the first in the Z-series of spacesuit prototypes designed by NASA specifically for planetary extravehicular activity. The Z-1 spacesuit includes an emphasis on mobility and protection for space missions. It features a soft torso versus the hard torsos seen in previous NASA EVA spacesuits, which provides reduced mass. It has been labeled the Buzz Lightyear suit due to its green streaks for a design. In 2014, NASA released the design for the Z-2 prototype, the next model in the Z-series. NASA conducted a poll asking the public to decide on a design for the Z-2 spacesuit. The designs, created by fashion students from Philadelphia University, were technology, trends in society, and biomimicry. The design technology won, and the prototype is built with technologies like 3D printing. The Z-2 suit will also differ from the Z-1 suit in that the torso reverts to the hard shell, as seen in NASA's EMU suit. PXS. NASA's prototype exploration suit, like the Z-series, is a rear-entry suit compatible with suit ports. The suit has components which could be 3D printed during missions to a range of specifications, to fit different individuals at changing mobility requirements. Mark III. The Mark III is a NASA prototype constructed by ILC Dover, which incorporates a hard lower torso section and a mix of soft and hard components. The Mark III is markedly more mobile than previous suits, despite its high operating pressure, which makes it a zero pre-breath suit, meaning that astronauts would be able to transition directly from a one-atmosphere, mixed gas space station environment, such as that on the International Space Station, to the suit without risking decompression sickness, which can occur with rapid depressurization from an atmosphere containing nitrogen or another inert gas. I-suit. The I-suit is a space suit prototype also constructed by ILC Dover, which incorporates several design improvements over the EMU, including a weight-saving soft upper torso. Both the Mark III and the I-suit have taken part in NASA's annual Desert Research and Technology Studies field trials, during which suit occupants interact with one another and with rovers and other equipment. SpaceX spacesuit. As of February 2015, SpaceX is developing a spacesuit for use by private astronauts to use in the Dragon V2 space capsule. Biosuit. Biosuit is a space activity suit under development at the Massachusetts Institute of Technology, which as of 2006 consisted of sevelau low-leg prototypes. Biosuit is custom-fit to each wearer, using laser body scanning. The MX2 is a spacesuit analog constructed at the University of Maryland's Space Systems Laboratory. The MX2 is used for manned neutral buoyancy testing at the Space Systems Lab's Neutral Buoyancy Research Facility, by approximating the work envelope of a real EVA suit without meeting the requirements of a flight-rated suit. The MX2 provides an inexpensive platform for EVA research compared to using EMU suits at facilities like NASA's Neutral Buoyancy Laboratory. The MX2 has an operating pressure of 2.5 to 4 psi. It is a rear-entry suit featuring a fiberglass hut, air LCVG cooling, water and power are open-loop systems provided through an umbilical. The suit contains a Mac Mini computer to capture sensor data such as suit pressure, inlet and outlet air temperatures, and heart rate. Resizable suit elements and adjustable ballast allow the suit to accommodate subjects ranging in height from 68 to 75 inches, and with a weight range of 120 pounds. North Dakota suit. Beginning in May 2006, 5 North Dakota colleges collaborated on a new spacesuit prototype funded by a USD $100,000 grant from NASA, to demonstrate technologies which could be incorporated into a planetary suit. The suit was tested in the Theodore Roosevelt National Park, Badlands of western North Dakota. The suit has a mass of 47 pounds without a life support backpack, and costs only a fraction of the standard USD $12 million cost for a flight-rated NASA spacesuit. The suit was developed in just over a year by students from the University of North Dakota, North Dakota State, Dickinson State, the State College of Science and Turtle Mountain Community College. The mobility of the North Dakota suit can be attributed to its low operating pressure, while the North Dakota suit was field-tested at a pressure of 1 psi differential. NASA's EMU suit operates at a pressure of 4.7 psi, a pressure designed to supply approximately sea-level oxygen partial pressure for respiration. AUDA-X. Since 2009, the Austrian Space Forum has been developing AUDA-X, an experimental Mars analog space suit focusing on an advanced human-machine interface and on-board computing network to increase situational awareness. The suit is designed to study contamination vectors in planetary exploration analog environments and create limitations depending on the pressure regime chosen for a simulation. since 2012, for the Mars 2013 analog mission by the Austrian Space Forum to Erfoud, Morocco. The Auda X analog spacesuit has a sister in the form of Auda S. This is a slightly less sophisticated suit meant primarily to assist Auda X operations and be able to study the interactions between two astronauts in similar suits. The Auda X and Auda S spacesuits have been named after the fictional princess from the Jules Verne's 1873 novel Around the World in 80 Days and can be followed on Facebook. A public display mock-up of Auda X is currently on display at the Dachstein Ice Cave in Obertraun, Austria, after the experiments done there in 2012. NASA Constellation Space Suit System. On August 2, 2006, NASA indicated plans to issue a request for proposal from the design, development, certification, production, and sustaining engineering of the Constellation space suit to meet the needs of the Constellation program. NASA foresees a single suit capable of supporting survivability during launch, entry and abort, zero-gravity EVA, lunar surface EVA, and Mars surface EVA. On June 11, 2008, NASA awarded a USD $745 million contract to Oceaneering International to create the new spacesuit. Suit ports. A suit port is a theoretical alternative to an airlock, designed for use in hazardous environments and in human spaceflight, especially planetary surface exploration. In a suit port system, a rear entry spacesuit is attached and sealed against the outside of a spacecraft, such that an astronaut can enter and seal up the suit, then go on EVA, without the need for an airlock or depressurizing the spacecraft cabin. Suit ports require less mass and volume than airlocks, provide dust mitigation, and prevent cross-contamination of the inside and outside environments. Patents for suit port designs were filed in 1996 by Philip Culbertson, Jr. of NASA's Ames Research Center and in 2003 by Joerg Bocher, Stephen Ransom, and Frank Steinziak. Astronaut Glove Challenge. There are certain difficulties in designing a dexterous spacesuit glove, and there are limitations to the current designs. For this reason, the Centennial Astronaut Glove Challenge was created to build a better glove. Competitions have been held in 2007 and 2009, and another is planned. The 2009 contest required the glove to be covered with a micrometeorite layer.